Okay, so don't want to take anything for granted. Maybe you've done a lot of this just last semester. I think maybe there might be one or two things you can pick up here that you still might find useful. And if you're not quite sure about your factoring this, then that's why we're doing it. It comes up pretty often. It has a lot of applications that we'll see pretty soon, I think. So let's just start right away. We recently talked about multiplying, polynomials and other similar expressions that have variables in them. And this is kind of like multiplying, but going backward is what factoring is. So I want to do at least one or two of each of these. And number 4, I'm going to say a little bit more about that. There are more options here than you might remember or know exactly how it works, and sometimes it's really convenient to do it this other way that's easy to forget about. But anyway, let's just start from the top of the list. The largest common factor. So I'm just doing from the R4 section. These are all book problems. So R4, number 4. Every single one of these says to factor, and some of them come in subsections where it specifies which method to use. But what are we doing here? We've got 12m squared plus 3m to the 6th. Well, we have 2 copies of m that both of them have in common. There's also maybe a constant that's going to go right here. So left the blank space for now. But the first thing that jumps out is, well, we've got powers of variables. The biggest one is the second power of m. And no other variables. But we do have, they're both divisible by 3, and this one's exactly 3. So that's 3m squared times 4. And there are no more m's left over. So that one's done. We took out the 3, we took out an m squared. But 6, we removed 2, we've got 4 left over. So you can always check your work. I didn't know what this was, I had to figure it out. Factoring is kind of the harder problem. Just distributing is, well, we just multiply, we get this one, we multiply, and we get that one. So if you're really good at R3, you're really good at multiplying, then factoring, well, you multiply it out again to check your answer, and everything should add up to what it's supposed to be. And then that's so that's it. It's important. Here's another one that's a little slightly. It's also fun taking out the Grace-Kahn factor, but it's separating the signal from the noise and figuring out what is. This one is a little bit kind of like pattern recognition. Actually, the book doesn't actually include a separate thing on this, but there are some things where, like, under the hood, the way I think about it is as a substitution. So what I'm saying here is that both of these have something in common, but it's the thing that they have in common is a really noisy expression with multiple terms. So if I had, one way to think about it is that if this is capital X, well, if I have AX plus C times X, then, if I have 2 X's and 3 X's, then I've got 5X total. And that's somehow easier to see than when it's this whole noisy B minus 2 thing. So if I had that, then sorry, it's not C, it's B minus 2. So this is how many copies of X? I have A plus C copies of capital X, which is, you don't have to invent a variable. If you can just sort of see this, then you can just sort of jump straight from the first line and put equals well, b minus 2 is the thing that every term has in common. Of the big expression, we've got a times b minus 2 plus c times b minus 2. So we have how many b minus 2's do we have? We have a of them and we have c of them. But the thing that they have in common, if it's easier for you to think about it, sometimes it just depends on how hard a time you're having or how much it helps you. Sometimes writing a little bit more, but it's easier to think about. Sometimes that's worth it, and maybe you should. That's what's happening with number 7. So this is these are both in the book were sort of listed under a list of problems of that type. Where you just take out the largest common factor. The largest common factor is b minus 2. And that's what you end up with. All right, so number 2, or technique number 2. So this is technique 1. And this one, I guess technically, the book doesn't have a whole section devoted to this, but the way that's easiest for me to understand what we just did there is with this other technique that I'm calling technique number 5. And that's what we're doing here. So now, technique number 2. Technique number 2 kind of makes a comeback in something later in this section number 4, or this technique number 4 that we'll do. But anyways, grouping. So in review for problem number 9, we've got 3x cubed minus x squared plus 18x minus 6. So what do we get here? So by grouping, whenever you have just 4 terms, I think you group whatever you want, but as long as you don't group the highest power with the lowest power, I think anything else will usually work out fine. But usually you just take in decreasing order, or maybe 2 terms in the middle have the exact same order. Sometimes that comes up, and then grouping still is useful. If they want it to be simple, they'll already have it in 4 terms split up, and they won't combine anything because they want you to see the pattern. So here, you just take the 2 groups. You take the first group, you find the greatest common factor. Both of them have an x squared. This one has 3x, so there's one more to get the x cubed. So you multiply, yes. You multiply, yes, it's that one as well. So that's perfect. So these two have a 6 in common. Well, this is 6 times 3, and there's an x for that term. This one, it's not positive 6, it's negative 6, so a negative 1. And just like this problem number 7, and that's kind of a warm-up for this kind of problem. These 2 things have, maybe if you do a couple of these, you start to see the pattern and you realize, well, the thing that they have in common now is this expression has a 3x minus 1 for both terms. And how many 3x minus 1s? We have x squared of them, and we also have positive 6 of them. And yeah, that's kind of it for that one. I almost have enough space to do one more, but not quite. I guess we'll just flip it over. So another factor by grouping. So again, by grouping, number 14. So again, the instructions just say factor 5a cubed minus 10a squared plus 25a. Just trying to make the a a little bit bit more presentable. Minus 50. So factor this by grouping. So both of those are divisible by 5 and no more than that. This one is just one more power of a, but then there's 5 is the entire thing. This other one, it's negative 2, and then a squared is already a squared. This other one, 25, let's see, that's times a. And if these are the same thing, then factoring by grouping works. If these two factors have nothing to do with each other, then factoring by grouping failed, and you can't really do much with it. But luckily, we have something good here. So 5a squared okay, so these things, both of them have an a minus 2 in common. Well, how many a minus 2s do we have? We have 5a squared of them, and then we have another 25 of them. But we can actually go a little bit further. And the book says, the book calls this like synthesis, I guess is what their name for this is, when you do more than one method. So this is like technique 6. We did one thing, but we keep going. They call it synthesis, and that's when you do one thing and then you see another pattern and you keep going with it. Well, what do we have here? We have 5 times a squared plus 5. So maybe that's a little bit better. Looks pretty good to me. So depending on how you do it, you could at very step number 1, you could factor out a 5 out of the whole thing. You would have some middle steps, and then if you factor out the 5 out of the whole thing at step 1, and then factored the middle part, this is what you would get left over. It's kind of, if you do lots of correct steps and you just keep factoring, maybe there's more things to factor as you keep going, and you eventually get to the same destination, because equal sign means it's equal, it's the same thing. It's just how did you break it into pieces? How many steps did it take? Well, we got 3 things, so it's like a couple of different steps, and you'll eventually get here if you do everything, if you make nothing but legal moves. So that's how you do it. Okay, so these are a lot of problems have been essentially reduced down to this. Well, what you want is like x plus p times x plus q. So are these equal to each other? So let me just sort of tell you sort of the general picture. This is kind of something you might already be familiar with, but you get x squared. Each of these get multiplied by each of these, so you get a qx, you get a px, and you also get pq. So there's this standard, there's this very famous thing. What are you looking for when you have a polynomial where the leading coefficient is 1 on the x squared term? What are you looking for? You want p plus q to equal b, and you want p times q to equal c. Can I find p and q? So if they give me this, can I find p and q? Big question mark. And that's what it sort of boils down to. If you can do that, then you write this down, you factor by grouping, and eventually you'll get something that looks like this. So, so that was a 1. It looks kind of like a 7. All right, so that's the general picture. So example, what did I pick this one here? All right. I didn't write down what problem number it is, but we'll just do it. P plus Q equals -7. So we know right away that we need negative. Well, we want a positive result, so they have to both be negative. So it'd be -10 times -1. We add those together, we get something way too big. -5 times -2. Yay, that does it. So we get W squared minus 5W minus 2W plus 10. If you have if this factors and then into two things that add up to the number of middle terms, to the coefficient on the middle term, then you break the middle term into those two numbers, and factoring by grouping should automatically always work. So factor out W minus 5. And then there's like, I'll just factor out the +2. Yeah, this is a little bit awkward, but if you did this, I just want to show you that you're not in trouble. You have to just figure it out. So that's a -W plus 10. Well, I don't like that. If I want to factor out a minus, I just take the negative of both of these. So this becomes a +W, and this becomes, sorry, I factored out the 2 though. I factored out the 2, so if I factor out a minus sign, yes, it would have been better if I had just skipped if I had just factored out a -2 in the first place, but you're not in trouble. It's a valid step that's not quite as useful as you want it to be. You wanted these two to match, but they're actually negatives of each other. You factor out a negative from the other one. Maybe the best practice is maybe you want the highest power of the variable to be positive, unless you have some other reason in mind to do something different. But usually I just like to have the highest power be positive. So what do we get? We have the W minus 5 is the thing that both of these have in common, and then how many of those do we have? We have W copies of W minus 5, and we also have -2 copies of W minus 5. And if you wanted to check your answer, you would multiply everything out. You would get the +10, the -2W, the -5W, the W squared, and so you get this expression, which is exactly the original thing. So that looks pretty good. So this step was just to show you that this is something that can be a little confusing. You might do that. It's not incorrect. It's just, it gets you, it's like half a step closer to the finish line, and then you have to figure out, well, what's going to help me actually get the rest of the way there. If it looks like almost the right thing, but it's a sign error, you just factor out a minus, and then you fixed it for yourself. And that's what this little moral lesson was about. So, all right, so here's where it starts to get a little crazy. Not too crazy, but there are like two ways of doing it. One is, a lot of times, like maybe somebody asks you how to do this like a year from now, and you haven't done it in a year, and you're like, oh man, I forget. And then sure, you just do it by guessing because you don't remember what the rule is. That's kind of okay. it's a little bit faster and it works a little bit easier with, especially with larger numbers where there's more things that you have to guess. If you have a system of doing it, a systematic way of getting to the answer a little bit faster. The bigger the numbers, the more techniques you'll want to involve to because these techniques they start to really pay off when you have big numbers. All right, so let me show you what I kind of mean here. So technique 4. So technique number 4, I'm going to use number 37. I'm going to just do it by guessing first. But then I'll show you a sort of systematic way that you can transform this into a factor by grouping problem. So factor by grouping, we did that with when the leading coefficient was 1. The PQ trick only works for that. There's a slightly modified P and Q for this kind of problem, but the original one doesn't work quite right that way. So the book calls this the FOIL method, which is basically you have some amount of x's, and then you have another, plus or minus something, and then you have some amount of x's plus or minus another thing. The first thing you might want to look at is the constant. So that means that the constants have to either be both positive or both negative. Well, if this negative were out, if there were a negative out front, you would want to factor negative out of the whole thing, which really cleans it up. So we really want a plus here. But once we've done that, we know we're only getting positives here, and we're getting positive times positive for the constant, because we don't want negative times negative, because then we know that we would get a negative here. So we're trying to figure out how many x's, and then these two constants, what do we get? Well, luckily this number is really small and doesn't have a whole lot of options. We know that we're getting a 2 and a 1. That's the only way to multiply and get 2. But then how many x's? We want this times 2, and then this times 1. And it has to be like either 4 times 3, or it has to be 6 times 2, or it has to be 12 times 1. Well, 12 times 1 will be way too many x's no matter what we do, so it's not that. 6 plus 2 times 2 would be not quite enough, but 4 times 3 has a chance. And it turns out, let's see, well, 4 and then 3 times 2 is 6 is not quite right either, but if the 4 goes here, it's 8x. And then 3 more is 11. So that was kind of this one was a little tricky. So it was like, well, we had to get exactly 11 x's, so we get 8x plus 3x. It took us there were like 4 or 5 different things I had to go through. Because we're doing lots and lots of different things. So this is kind of borderline. Maybe I wish I had a method instead of having to just write down the FOIL thing, just FOIL, like trial and error, like 5 different approaches here. So there is, if this is going to ever work, then there's a method that tells you how to do it by grouping. So let's do it by grouping. I'm running out of space here. I'm going to move it just to the side. I just wrote down the original thing again. So that was the answer we got. Well, the trick is, well, this is just something that some people figured out. So this is like solution 2 by grouping. So if you have ax squared plus, I think, what am I, do I just want to call it a? Yeah, ax squared plus bx plus c. There's a little tiny twist on it. So you want to figure out how do you group the middle term. You want to write ax squared plus px plus qx plus c. You want a times c, that a is the new thing that we didn't have before, to equal p times q, and p plus q to be equal to b. And that's just how it works out. It ends up always working out if you do that. That's the trick. And then you do factor by grouping with whatever's left over, and it always works out. If you can find a p and a q, if it's impossible, then you're not going to be able to factor it no matter what. But if you do find a p and a q, if it is possible to find a p and a q, then this will always lead to a factoring of your quadratic trinomial, 3 terms. So for this example, we had so p times q has to be equal to 24, and p plus q has to be equal to 11. So 8 times 3 is what's going to do it, actually. So 12 times, they have to both be positive, because double negative would give you a negative here. So positive, positive, everything's positive. 6 times 4 is going to be coming up just short. 8 times 3 is the magic way to factor this. So this is, if you had the big factor tree, you would end up getting 2 to the 3rd times 3. So you can get how many 2's get grouped with the 3. You could get 6 times 4, you could get 12 times 2, but 8 times 3 is the magic number. So 8 plus 3, where 8 times 3 is equal to 24, that's the smiley face. So we get 12x squared, and it doesn't matter. It's if you and your neighbor, if you wanted to group the 8x with the 12x squared, you'll get one answer. Your neighbor does it the other way around. The steps in the middle were different, but the final answer will be exactly the same. Just the different pieces will be flip-flopped, but they'll all end up in the right place at the end of the day. So sometimes in math, the question, well, which one goes where? Sometimes the answer is if you stay consistent, it doesn't matter which choice you made, just stay consistent. So what do we get? Well, we better get the same thing, because we already saw the correct answer just by guessing with the FOIL method. The first 2 terms, there's an x that they have in common. So we get 3x plus 2, because we want the 8x here. And the second one, this one, they have nothing in common. Well, they do have a 1 in common. So to be completely, if you don't write down the 1, I'll know what you mean. But just really just emphasizing the general pattern. Well, technically, you can always write a 1 times out front. And this really drives home the point that this is what you factor out. So you don't factor out nothing. You factor out the 3x plus 2. And this isn't 0 copies of 3x plus 2. This is 1 copy of 3x plus 2. Together with the 4x copies of 3x plus 2 that you already had. So that's kind of interesting. So maybe I'll say a little bit more about this in a separate video. I just want you to understand how do you do it. Why does it work is another question. but let's just do one more problem, and then this is basically what I need you to know how to do. No, actually, I think that's fine. I think I'll just leave it at that. So, yeah. So I think that's it. That's plenty long enough. We did basically one of everything. So yeah, good luck. If there are any questions, let me know about it. We can talk to each other in the discussions, or maybe another student might even be able to chip in. And don't forget, in Mind Lab, some of the videos might already address this. So there we go.